In the next 20 minutes, I will give a talk on a generic backend for exploratory programming, and this provides a way to test exploratory programming in a language-independent manner. And this is work I did for my master thesis together with my supervisor, Thomas van Binsbergen. So the traditional style of programming, where you edit your program, you compile it, and you run it, is well known. However, it gives a rather slow form of interactivity, because if you want to make a change, you have to edit the program, you have to compile again. And that compiling is really a bottleneck. It also gives a shallow form of interactivity, because you can only interact with the interface your program exposes. And if you need to test out a library function or maybe a function that is deep inside your program, it becomes a bit more tricky. You either have to add it to your interface or you need to work in a debugger. But there are different styles of programming, like programming via Read-Eval-Print-Loop or REPL programming. This gives you a style of incremental programming, where you submit small programs to the REPL and you get immediate feedback. So on the slide, you see an example where we define a hello function. We execute it, we get feedback. Then we redefine it in the same session. We execute it and we again get feedback, this time a different output. So this time we are not really dependent on that compile cycle. So we have a faster form of programming, and we can do a kind of style of exploratory programming, where you explore your problem domain via interacting with your program, submitting small snippets of code, extending functions, testing those functions in your REPL and seeing how they behave on different inputs. And that's how you can explore your problem domain and construct a system. There are also other type of interfaces to do this exploratory programming. For example, a notebook, which combines it with literate programming, since you can also put in documentation cells in a notebook. And this is very useful for people that are not really programmers, but still want to, for example, change variables and see the effects. And therefore, it's rather used a lot in data science and provides a nice alternative interface to share your work with. However, these interfaces are not always consistent. So on the slide, you see an interface of the J shell. So that is the here, that is the Java shell, so REPL for Java. And on the other side, you see a notebook for Java. And we can see that the notebook only gives output when we evaluate X, but the REPL gives output or feedback on almost every invocation. So you could argue that these two interfaces handle side effects differently, while that should be part of the executing, so the interpreter. Also, these interfaces do not implement valid Java. So these programs are not valid Java, but the interfaces can still execute them or evaluate them. And that's what you see more often with these kind of interfaces, is that they implement an extension on the original language. However, this extension is not always clear that this extension even exists. It's not always documented, or it's independently developed of the original language, resulting in fragmentation in the language tools. Such an extension is not always required. For example, with Python, you already get this style of incremental programming via the Python interpreter. To make the development of these interfaces clearer and more consistent, previous work gives a principled approach to constructing these type of interfaces. And this approach is based on a definitional interpreter. And a definitional interpreter is an interpreter that not only evaluates the program, but also defines its operational semantics. And with such a definitional interpreter, there becomes a clear difference between the base and the extension language, since there would also be a definitional interpreter for the extension language that then uses the base language. On the slide, you see an example of a extension on mini-Java, which is a subset of Java. And this extension adds to mini-Java the requirements to make it support REPL type programming. And for example, the set output comes from the mini-Java definitional interpreter, and that is then used by the extension language interpreter as well. So overall, such an extension language is rather small, but adds the requirements to provide style of incremental programming. And then with this approach, you can construct generic interfaces that use the same definitional interpreter. This then results in inconsistent, so consistent interfaces, and reusability of these definitional interpreters. And the approach also talks about exploratory programming via a exploring interpreter. So an exploring interpreter is built on top of the definitional interpreter, and it's basically just a bookkeeping machine that has a current configuration. So on the slide, we, for example, have the configuration where nothing is stored, in this case empty, and the configuration stores the state of the system. So if we execute x is 2, the configuration would now have it stored that x has the value 2. And what we see here is an execution graph. So an execution graph is a combination of configurations, and between configurations are transitions, which are programs. And this exploring interpreter then has 3 operations: the display operation, which gives a structured representation of this execution graph, as seen on the slide. Then we have the execute. So execute takes the current configuration and a program, and then calls the definitional interpreter, resulting in a new configuration. So in the slide, if we would be in the empty configuration, we would call execute with the program x is 2. Then the exploring interpreter would call the definitional interpreter with the empty configuration and x is 2. And as a result, it would get this new configuration where we have x is 2. The exploring interpreter then makes sure that the whole execution graph is updated and so on. Then there's also the revert operation, which provides an option to revert back to previous configurations. So on the slide, you see a difference between the 2 configurations. One is circular and one is a rectangle. The rectangle means it's the current configuration. So with the revert, we could, for example, make the empty configuration the current configuration. Then the method talks about different behaviors for these execution graphs. So a stack tree graph behavior. There's also the graph structure stack behavior. So with a stack, you always have one incoming and one outgoing edge in your nodes. With a tree, you can have multiple outgoing edges, but only one incoming edge. And with a graph, you can have multiple incoming and multiple outgoing edges. So here you see 2 examples, one of a tree and one of a graph. And this is based on an interaction with an exploring interpreter. So we start in the empty state. We execute the program x is 2. So we get into this state. Now we revert. So we revert back to the empty state. Then we execute x is 0. So we go here. And then we execute x is 2 again. And in the tree behavior, a new configuration is created for the x is 2. However, in the graph behavior, we see that the x is 2 shares the configuration that was already created on our first execution of x is 2. So this is the difference between the tree and the graph behavior. And in a graph, we have sharing of configurations between different transitions. Then this approach is based on sequential languages. And a language is defined as a structure where we have a set of programs, a set of configurations, an initial configuration, and a definitional interpreter that assigns for each program a function from configurations to configurations. So here's an example of a small while language, so a language with support for while loops. And we have defined that in Haskell according to the definition of a language. So we define a while interpreter, which takes a command, so that is the programs for this language, and then returns a function from configuration to configuration. A configuration is then a store and an output. And a store is a mapping from string to literals, and the output is just a list of strings. Then we have our initial configuration, which is the configuration with the empty store and the empty output. Then such a language is sequential if there's an operator, such that we can combine any 2 programs and get a new valid program. And if we execute the combined program via the definitional interpreter, it should result in the same effects of the same handling by the interpreter as executing the composition of the programs in isolation. And for the while case, we have a sequence as this operator. And then here we see that the equality holds. So therefore, while is a sequential language. And then what we try to do is use this sequential language definition to provide a generic exploring interpreter that can work for any language that follows this definition of a language. So to do that, we make the Explorer type a parameterized data type, where the parameters of this type are the programs and the configurations, so the programs and configuration. From this type, we can deduce the type signature of the definitional interpreter, the config, and the execution environment. So in the execution environment, we want to store configurations and programs, where programs are the edges and configurations the nodes. However, storing configurations directly can become quite messy, since configurations can get rather big, and if you have many, it's very difficult to operate. Therefore, we introduce a reference. So every configuration gets a reference, and then our execution environment or execution graph stores references as the nodes and then programs as the labels. And then we have a map that maps references to configurations. So this way, the execution graph shows references instead of full configurations, which makes interacting for the user a bit easier. Then we need to capture the different behaviors. So we do that via two booleans, where the sharing and backtracking. So sharing the nodes if sharing is enabled, and backtracking the nodes if backtracking is enabled. And this captures the four different behaviors. So when we have sharing and no backtracking, we have the graph. When we have no sharing and no backtracking, we have the tree. No sharing, backtracking, the stack. And with backtracking and sharing, we have the graph structure stack. Then this is the full definition of our exploring interpreter that is language independent. And then we have the smart constructors to construct such an exploring interpreter. And this then takes a definitional interpreter, which is given by the function type here, and a configuration, which is given by, and then returns an explorer that is typed by the programs and the configurations, and these are deduced from the types of the definitional interpreter. And the make explorer smart constructor just sets up the execution graph, assigns the initial configuration a reference, and adds it to the execution graph. Then we have the three operations. So the revert operation takes a reference and an explorer and returns a maybe explorer. So the maybe is required because the reference could be that the reference does not reference a valid configuration, so then nothing is returned. And otherwise, when it is a valid configuration, a new explorer is returned where the current configuration is the configuration reverted to. And if backtracking is enabled, the configurations, the future configurations, so to say, are destroyed. And the execute function takes a program and an explorer and returns a new program. So this calls the definitional interpreter with this program and the current configuration, resulting in a new configuration. And then if sharing is disabled, it always creates a new reference and adds the new reference to the execution graph. However, if sharing is enabled, the execute operation first looks through the execution graph to see if there already is a configuration that is equal to the configuration that just resulted from calling the definitional interpreter. And if such an equal configuration is present in the execution graph, then a transition between the current to the existing is created instead of a full new configuration. Then there's also the display operation that just gives a structured representation. This could be a JSON or a dot diagram and so on. It is important that it's there because it provides a way for the user to interact with the execution graph. So we still have one problem, and that is that our exploring interpreter it doesn't have that much information. It only has the language definition, and it doesn't know what the sequence operator is in a language. So if we call the execute action with a sequence program, the explorer happily executes it, but it only results in one transition, as we've seen on the slide. However, it's a sequence of programs, so it could also be two transitions. But because we don't know what the sequence operator is, the exploring interpreter has no knowledge on how to unpack such a sequence program. To work around this, we look at the fault right type signature, and we can see a perfect match for our execute operation. So what we do is we expose an execute all operation that takes a list of programs and then calls the execute function on that list via fault right. This then requires the interface to do the unpacking for us, but the interface doesn't have to do this fault right itself. So now that we have this exploring interpreter defined, we can explore it, and we can look at possible extensions and how it works. So the nice thing about this implementation is that it's language independent. So we can try out imperative languages, functional languages, and we can try out different interfaces. There are a couple of paths to explore them. For example, the handling of side effects. In some cases, like in our example, we store the output in the configuration, but in some cases, it's also beneficial to abstract away the output. So for example, the print statements via monad, because when you store the output in the configuration, sharing becomes very minimal, because output can make a configuration different. So the whole configuration is equal except the output. So if you take away the output, you have sharing, but if you put the output in, you don't have sharing. So a nice abstraction would be to abstract such output via a monad. And this can be done by making the execute operation return the explorer in a monad. Another part to explore is debugging. So it would be nice to debug your exploring session. For example, on the slide, you see a exploring session where we start from our initial configuration, we execute exists null, and then we execute a while loop. But this while loop is only one program, so we get one iteration. But when debugging, it might be nice to actually explore this while program, so inspect this transition in more detail and see how the different iterations, what the configurations are after every iteration. Then the question is how to make this language independent and have a nice way for the user to interact with the execution graph, to not always show all configurations, but only when the user wants to inspect it. Another question is interfaces. So do all kinds of interfaces work? For example, notebooks, REPLs, and so on. And how do the interfaces interact or work with the different exploration behaviors? Are all kind of behaviors usable in different kind of interfaces, or are certain behaviors better suited to the other kind of interfaces? And does our explorer expose everything required for interfaces to operate nicely? So we are working on a evaluation of the exploring interpreter as well. This is done with FLINT, which is a executable norm specification language. And there we evaluate with 3 different types of interfaces. So we have a notebook or a web-based interface where the user interacts with the system via the web. We have a REPL interface, and we have a TCP service that can explore certain situations and then result in a sequence diagram as seen on the slides. So currently we are doing an evaluation of the exploring interpreter with these 3 types of interfaces. So the implementation opens up exploration of the exploring interpreter in a language independent manner. And now it's the goal to see how this can be extended further and what the fully usabilities are of a generic exploring interpreter. Thank you for your attention.
Thank you. If you could raise your hands, and then I can hand over the microphone. Peter.
Oh, my camera is off.
On stage.
Yes, here I am. Hi, Damian. Thank you for your talk. Could you please go back to the previous slide, because it's, I'm not sure if you can zoom in on it, but it was really, I really couldn't read what's on the slide. Is it possible to zoom in?
I don't think it is. No, if I move. No, it's not really possible. I can maybe, so it's more meant that to show the three different types. So the middle one is a command line. So it's just a REPL where you can put in programs.
Okay.
And then here we have a web-based interface. So just in the web browser. And then we have 3 different types of outputs. So we have the frames here, we have the scenarios, And then you can run different scenarios and see that in your output.
Okay. And what does the scenario look like? Sorry.
So in this case, you could, for example, so that is what is done here. You could, for example, say that there is a seller named Alice, and there is a buyer named Bob, and then there is a certain amount on an asset, and then this is executed, and it results in, that's maybe more visible here, and that then results in certain interactions with the system. So in this case, I can't zoom in, unfortunately, because there are images. But in this case, the system makes an offer to the seller, and it can receive the offer via the buyer, which then say, okay, I accept it. And then certain requirements are set in the system, which have to be true for it to be a successful buy.
Okay, and this is also automatically generated then?
This interface, this sequence diagram, yes.
Ah, okay. Okay, thank you.
You're welcome.
Hi, Damian.
Hi.
Thank you for the presentation. You started off by saying, I need a system if my compiler is very slow, because then I need an interpretation system. But if I see your presentation, there are many more advantages than just the speed of reacting. Is that true, or is it just?
Yeah, that's true. No. So with the REPL, you have a very small form of exploratory programming. So you can execute a snippet and you get immediate feedback. But there was a study done on the most REPLs, and many REPLs do not even implement a redo feature. So with the exploring interpreter, you automatically already get that redo feature. And many more features. So the idea of moving away from the edit compile cycle is the basis for this idea. And then it's extended via this exploring interpreter. So it extends the features you see in normal REPLs.
John, your question?
Hi, Damian. So I didn't really understand the difference between the tree and the graph-shaped state spaces that you showed us from the point of view of the user of the REPL. I mean, does it mean that the revert operation behaves differently if you're using a graph or a tree? I understood that you said that you get sharing with the graph, but these states are immutable, aren't they? So why does sharing matter to the user?
They are indeed immutable, but so with the tree and the graph behavior, the revert is the same, but the execute is different. And with the stack, the revert is different. So with the stack, it would destroy the other configurations on the revert. And with a tree and a graph, you do not have that. And on the slide, you see that here we create a new configuration with the tree behavior. But in the graph behavior, we reuse that existing configuration.
But why does that matter to the user? You end up in the same configuration, right?
You do end up in the same configuration, but it's a different path.
Is the path visible to the user once they're in that configuration?
So it can, for example, expose this, well, in this case, this dot diagram, but it can see a structured representation of this graph. And then you would see the different kind of behaviors. And one thing about the tree behavior is that you always have one incoming edge.
Yes, that's why I wondered whether revert might behave differently.
Yes. That is one thing, because when you are in this node and you do a revert to, for example, the empty configuration, there are two paths that we can take to that empty configuration. And that is one difference of the graph behavior that we have in there.
And what difference does it make which path you follow?
In some cases, interfaces want to print out effects that are removed on a revert. So, for example, if you have something that does a revert from this to this, you would print that x2 is removed. And then you would have x is 0, but if you would take this path, you would only have x is 2.
Sorry.
Hi, Damian. Nice talk.
Hi.
I wonder how far this scales if you think about larger code bases. I mean, I see this for small snippets, like a couple of lines easily, but how if you have a real code base?
So, that's a good question. We need to explore that further, because when you start your code base and you load in a function, that needs to be part of your configuration as well. So the idea is that if you explore your system, you do it in small sessions, and then you hopefully do not get too big of a system, but indeed there could be some issues that configurations get rather big. We do not have a definitive answer on how usable it is then.
Could I just move to some spot in my code and basically do the REPL loop within this context in which I am there?
Yeah, but that is not part of the exploring interpreter.
Okay.
So that would be from the interface, and then you could, for example, load in your program and then execute one function. But that still requires that it's part of the system.